Aslamoalikum. Next step after formulating problems is to look for their solutions. In lecture number 9, we will solve problems by searching. This is today's agenda. Now that we have studied how to formulate problem and how to formally document problem, we are now in position of looking for solutions to effectively be able to solve the problems. For solving problem in AI, searching techniques are used. Search trees and graphs can be generated for every problem in AI by connecting initial state to the successor functions that can finally lead to goal. We can use search trees that can be generated with initial states and successor functions, and we can draw very good graphs, and then after drawing graphs of every problem, we can apply search techniques to those graphs. We will use uninformed search strategies. As problems can be shown in form of trees and graphs, the searching algorithms can be used to search for goal state. Many search strategies can be used to solve problems. One of these is uninformed search strategy. This is named uninformed as it doesn't have additional information or heuristics that might help in reaching goal. It blindly searches for the solutions based on search algorithms. It only uses the information available in the problem definition. No other information is provided. These are types of uninformed searches. We will study breadth first search, depth first search, uniform cost search, depth limited search, and iterative deepening search. In today's lecture, we will focus on breadth first search. These are the criteria on the basis of which we can compare search strategies. Search strategy can be compared on the basis of completeness, time, space, and optimality. A search algorithm is said to be complete if whenever at least one solution exists, the algorithm is guaranteed to find the solution within a finite amount of time. This is time complexity. The time complexity of a search algorithm is an expression for the worst case amount of time it will take to run. The maximum amount of time that it will take to run is known as worst case amount. It is expressed in terms of maximum path length, which is M, and maximum branching factor, which is B. M depicts the maximum path length, and by B we mean maximum branching factor. We will come to these details in coming slides. The space complexity of a search algorithm is an expression of the worst case amount of memory that algorithm will use. It is also expressed in terms of M and B. Obviously, optimal solution is that out of many solutions, there is only one best possible solution. The answer to optimality is, will the optimal least cost solution be found by this algorithm or not? On these 4 parameters, we will always compare the algorithms of searching. Time and space complexity are measured in B, maximum branching factor of the search tree, and M, maximum depth of the state space search. Let's look at these concepts using an example. Maximum branching factor is maximum number of children a node can have in a tree. In this example, the initial root node S has the maximum number of children, which are 4. A, B, C, D. These are 4 children of S. Thus, the branching factor of this complete tree becomes 4. Maximum depth of tree is maximum path length that a tree has from root to its leaf nodes. Leaf nodes are those nodes that do not have children or child. Here, here, here we have 5 leaf nodes E, G1, B, G2 and H. These nodes do not have any children. In this example, maximum path length from root S is towards G2, which is 1, 2, 3. Depth is calculated by counting the links between the nodes. We count these arrows that are between the nodes to calculate the depth of the tree. The maximum depth of the tree becomes the M, which is 3. 1, 2, 3. This is the longest path. We count the arrows on the longest path and say that this is the depth of the tree. Now let's discuss the simplest form of uninformed search called breadth-first search. As the name suggests, this search moves by expanding search width-wise of the tree. It makes use of queue data structure to store nodes as it moves forwards. Alright, we know it expands in the width of the tree. It uses the expansion level-wise, and we use the FIFO first in first out queue data structure for this. Let's discuss BFS using a simple example. Here we have a tree with 7 nodes A, B, C, D, E, F and G. We will perform BFS on this tree. For BFS, queue data structure is required. This arrow shows the front of the queue that we will use for this example. The front of queue is this. This is the starting point of queue. A simple rule of thumb is to move from root, then to left child and then to right child. We will follow the same searching structure throughout this course. First, we will look for root, then we will move towards left and then right. Root, left, right. By following this rule, firstly, node A would be inserted in the queue. We will insert node A in the queue as it is root. After A, we will insert B in the queue, as after root we have to look for left child following root, left, right regime, and B is the left child of A. B will be inserted in the queue. Once B inserted, we will look for right child of A, which is C, and we will insert C in the queue. Now, A will be removed from the queue as all of A's children have been traversed and there are none left to be searched. A had 2 children, B and C, and they are traversed and are inserted in the queue. Now, D would be added in the queue as it is the leftmost child of B. Now we would go on adding E in the queue as it is the right child, and by this point, all of the children of B have also been traversed. None is left to be traversed. At this point, B would be removed from the queue as all of its children have been traversed and control will be handled to C. Now C will become the root and F and G will become the left and right child respectively. First node would inserted be F, as F is the left child of C, and after inserting F, the last node inserted would be G, as G is the right child of C. By this point, whole tree is traversed. All nodes have been searched or visited. This is complete traversal sequence of tree using breadth-first search. First, node A will be visited, then B, then C, then D, E, F, G. This is the sequence in which breadth-first search works for this example. These are tree levels. Root node is always at level 0. This tree has 3 levels, 0, 1, 2, which counts to 3. A is root node, F and G are leaf nodes. Maximum depth of this tree is 2 and maximum branching factor is 2 as well, as we have 2 children at max for every node. BFS algorithm is complete if branching factor is finite. If branching factor is infinite, in that case result cannot be ensured and BFS might get stuck at one level and might never reach the next level where goal exists, as it searches the tree level-wise. This is the time complexity for breadth-first search. Here B is the branching factor and M is the maximum path depth. Space and time complexity of BFS is exponential. That might lead to computational explosion in case of infinite branching factor. Space and time complexity for BFS are same, which is B raised to power M branching factor raised to maximum depth of the tree. Obviously, breadth-first search is not optimal. It is not guaranteed to give you the best possible solution. The goal returned might not be the best possible solution of the problem. Alright, we will discuss when BFS is appropriate and when BFS is inappropriate. BFS is appropriate when you are sure that solution exists in the spread of the problem, as it searches the tree level-wise. If solution of problem existed in the depth, then BFS is not a good option because it would traverse the depth of the tree much later than it would traverse the breadth of the tree. BFS takes much space as it stores every node. And if your space is limited, then using BFS is not advisable. When space is limited, you must not opt for BFS. If solutions are in depth of the tree, then it must not be used. We learned from BFS that memory is a bigger threat than execution time. And for large trees, having larger depths and branching factors, use of BFS must be avoided. BFS is appropriate for smaller tree searches. This ends this discussion for today. Thank you.